Hello everyone. So in this lecture we will see some theorems on chi-square distribution. Before starting these two or three theorems in this lecture, I would like to say that before watching this lecture, just go through the transformation. That's Jacobian transformation. That is Jacobian transformation. Where will you find this topic? This topic is in your integral. That's integration basically. In double integral, you will find this topic, Jacobian transformation. Clear? Just go through that topic once, then come back to this lecture and see what's going on, what we will see in these theorems. So let's start the theorem number 1. That is the theorem is simply if x1 and x2 are two chi-square, are two independent chi-square variates, with n1 and n2 degrees of freedom respectively. Then the theorem says that ratio of x1 to x2 is a beta second kind, n1 divided by 2, n2 divided by 2 parameters. So these are the parameters of beta second kind. As you know from the continuous distribution that whenever we have beta, this is, let's suppose, A, this is, let's suppose, B. So A and B are my parameters for beta 2 distribution. Clear? So the relation between chi-square and beta is that if x1 follows chi-square with n1 degree freedom and x2, that's also a chi-square variate with n2 degrees of freedom, then the ratio of x1 divided by x2 is a beta second kind, n1 divided by 2 comma n2 divided by 2, and these two are my parameters. As you remember, if x follows normal 0 comma 1, x1 follow normal 0 comma 1, x2 follow normal 0 comma 1, then the ratio of x1 to x2 follows Cauchy 0 comma 1. Same, we can prove this by the transformation. Also we can prove this by Jacobian transformation. Here we are using again the Jacobian transformation. I hope कि आप लोगों ने ये किया होगा नॉर्मल के केस में, जब हम कंटिन्यूअस डिस्ट्रीब्यूशन पढ़ते हैं या जॉइंट डिस्ट्रीब्यूशन पढ़ते हैं तब आपने ये किया होगा. नाउ लेट्स सी इन दिस कि हम यहाँ पे क्या करेंगे. सी प्रूफ. सिंपली देखो प्रूफ कितना इजी है, बिल्कुल इजी है. देखो x1 किसको फॉलो कर रहा है, chi square with n1 degree of freedom. So f of x1 क्या होगा मेरे पास, that's 1 upon 2 n1 divided by 2 n1 या gamma n1 divided by 2 e raised power minus x1 divided by 2 x1 n1 divided by 2 minus 1, where x1 जो है वो greater than 0 है, less than infinity. Clear? ये है मेरे पास f of x1. So what will be my f of x2? That is simply 1 upon 2 n2 upon 2 gamma n2 upon 2 e raised power minus x2 upon 2 x2 n2 upon 2 minus 1. So ये है मेरे पास x2. So see, अगर हम इनका joint लिखेंगे, what will be the joint? That is f of x1 comma x2. As see, remember this is already given that x1 and x2 are my independent. x1 and x2 are my independent or two independent chi-square variate. So I can write this as joint will be the product of marginals. Clear? So I can write this as 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 n2 divided by 2 e raised power minus x1 plus x2 divided by 2 into x1 n1 divided by 2 minus 1 x2 n2 divided by 2 minus 1. So the range will be between 0 to infinity. Is this clear to you? What I did here, I simply wrote the joint distribution of x1 and x2. That will be the product of marginals, and and the joint distribution of x1 and x2 will be like this. Clear? Now see, we have x1 given x2 follow beta 2 n1 divided by 2 comma n2 divided by 2. We need to prove this. Clear? So let's make a transformation. Let u is equal to x1 given x2 and v will be x2. Clear? So see, this is my v is equal to x2, u is equal to this. Then replace x2 with v. So u is equal to x1 divided by v. So uv is equal to x1 and x2 is equal to v. So now to find the Jacobian, that is partial differentiation of x1 comma x2 with respect to u comma v. So this will be equal to del x1 upon del u, del x2 upon del u, del x1 upon del v, del x2 upon del v. Clear? So what is del x1 upon del u? So dx1 must del x1, that's partially differentiation of del x1 with respect to u. u का differentiation कितना होगा 1. तो यहाँ पे क्या बचेगा, v तो constant है तो बाहर आएगा, del u upon del x1 is 1. So ये आएगा मेरे पास v. So del x2 upon del u यहाँ पे तो नहीं है, del x2 upon del, यहाँ पे एक काम भी कर सकते हो, यहाँ पे this is del x1 upon del u, this is del x1 upon del x2 upon del u dx2 upon del v. ये भी आप कर सकते हो. हाँ, now dx1 upon del v, that's equal to u, and del x2 upon del v, del x2 upon del u, that's 0. That's 0 क्योंकि ये कांस्टेंट है ना, देखो x2 के रेस्पेक्ट में ये कांस्टेंट है तो 0 होगा ना, डिफरेंशिएशन ऑफ कांस्टेंट इज 0 और इसका 1 होगा. तो यहाँ पे हमारे पास क्या आएगा, क्रॉस मल्टीप्लाई डिटरमिनेंट निकालो तो क्या आएगा, v आएगा, ओनली v, मॉड ऑफ v. दैट जैकोबियन हमेशा हम मॉड में लिखते हैं, दैट्स मॉड ऑफ v. नाउ देखो ट्रांसफॉर्मेशन जब हम ट्रांसफॉर्मेशन करते हैं किसका, न्यू वेरिएबल का, दैट्स f ऑफ u comma v is equal to old variable into Jacobian. Clear? What's old variable? Old variable क्या है हमारे पास, that's 1 upon 2 n1 plus n2 upon 2, joint है ना वो, gamma n1 divided by 2 gamma n2 divided by 2 e raised power minus x1 plus x2 divided by 2 x1 n1 divided by 2 minus 1 x2 n2 divided by 2 minus 1. और ये क्लियर है. नाउ देखो हमने x का क्या लिया था अगर मैं आपको बताऊं कि हमने x1 गिवन x2 लिया था u और x2 लिया था v, तो यहां पे रिप्लेस करो, x1 is equal to u v, यहां से है ना. सो रिप्लेसिंग दीज वैल्यूज by uv and v in this equation, into Jacobian भी है ना साथ में, हाँ, in this equation. तो say this will be equal to 1 upon 2 n1 plus n2 upon 2 gamma n1 divided by 2 gamma n2 divided by 2. What's x1? That's uv. What's x2? That's v divided by 2. What's x1? That's uv. That's uv. n1 divided by 2 minus 1. What's x2? That's my u. Sorry, x2 is v. That's v. n2 divided by 2 minus 1 into Jacobian, that's v. Clear? Now see. This is equal to 1 upon 2 n1 plus n2 upon 2 gamma n1 by 2 gamma n2 by 2. Now see, e to the power minus can we take v as a common? So यहाँ पे क्या बचेगा? u plus 1, v तो common लिया ना, v divided by 2. Clear? Into u n1 divided by 2 minus 1, v n1 divided by 2 minus 1 plus n2 divided by 2 minus 1. यहाँ हम सीधे इसको ऐसे लिखेंगे पहले. This is v n1 divided by 2 minus 1 and this is v n2 divided by 2 minus 1 into v1. क्योंकि ये v है ना, mod of positive v is v. This is v1. So what will we get now? This is 1 upon 2 n1 plus n2 upon 2 gamma n1 divided by 2 gamma n2 divided by 2 e raised power minus v u plus 1 upon 2. So this is u n1 divided by 2 minus 1 and this is v n1 divided by 2 plus n2 divided by 2 minus 1. So this is simply v n1 plus n2 divided by 2 minus 1. Clear? So v u comma v is between this and this. So this is your new function, that's f of u comma v. This is your new function. This is your new function, that's new function f of u comma v. Now if we take marginal of u, see here is a concept that's the concept is that if you are given with f of x comma y, let's suppose this is some function, if you need marginal of x, then integrate with respect to y. If you need marginal of y, then integrate with respect to x. This is the opposite. If you need marginal of x, what's marginal of x? That is simply f of xx, single function. What's marginal of y? That's f of yy. Clear? This is a simple concept here. Now say we have the function that's a joint distribution function, that's f of u comma v is equal to 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2 e raised power minus v 1 plus u upon 2, that's u n1 divided by 2 minus 1 v n1 plus n2 divided by 2 minus 1, and this is between 0 to infinity. Now if you need marginal of v, that's let's suppose g of u, or if we need the marginal of u, that's marginal of u, and what's u? U is x1 divided by x2. So we basically need the distribution function of this, that's marginal of u, right? So say See, g of u will be integration from 0 to infinity whole distribution function. Clear? So we need a g of u. So the term involving u will be our constants. We will differentiate, this is dv, we will differentiate with respect to v only. As whenever we need the distribution function, marginal distribution function of some random variable, we integrate with the opposite random variable. That's if we have the f of x comma y, we need the marginal of x, we differentiate, we integrate with respect to y. So say now what will happen here? So this is constant 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2. And see, this will come out as the constant, that's u n1 divided by 2 minus 1. Clear? Multiply 0 to infinity e minus v 1 plus u upon 2 v n1 plus n2 divided by 2 minus 1 dv. So we need to integrate this function. We need to integrate this function. As you know, 0 to infinity e raised power minus ax x n minus 1 dx. What is this? This is equal to gamma n divided by a raised power n. Simply, this is simply a function, that's a gamma function. This is a gamma function. Treat this as n and this is my a, this is x. So the integral, this is equal to this. So this is equal to 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2 u n1 divided by 2 minus 1. Then what will be the value of this integral? That will simply gamma n1 plus n2 divided by 2 divided by a. What's a? A is 1 plus u upon 2 n1 plus n2 divided by 2. Clear? So this is the function that we get from these results. So now if I write it in the beta function, that will be equal to 1 upon beta n1 divided by 2 n2 divided by 2 u n1 divided by 2 minus 1 upon 1 plus u n1 plus n2 divided by 2 du, and this is between this and this. See, if I expand beta a comma b, that will be equal to gamma a gamma b upon gamma a plus b. So see 2 n1 plus n2 divided by 2, and from this 2 n1 plus n2 divided by 2 will be cancelled outside. We will be left with only this term. So this is my f of u, that is f of x given y. F of x given y will follow beta 2 n1 divided by 2 comma n2 divided by 2. Hence proved. Clear? Hence proved. Now second theorem is that is if x1 and x2 are independent chi-square variates, with n1 and n2 degrees of freedom. If x1 and x2 are my independent chi-square variates with n1 and n2 degrees of freedom, then u is equal to x1 plus x2, and v is equal to x1 plus x2 are independently distributed as beta first kind n1 divided by 2 comma n2 divided by 2 with, or simply we need to prove this, or simply if I write this, prove that x1 plus x2 will follow beta first kind n1 divided by 2 comma n2 divided by 2. We need to prove that u is equal to this will follow beta first kind n1 divided by 2 comma n2 divided by 2, right? So this is u is equal to this will follow beta n1 divided by 2 comma n2 divided by 2. In previous theorem we simply prove that x given y follow beta 2 n1 divided by 2 comma n2 divided by 2, and in this term we will see x plus y will follow beta first kind n1 divided by 2 comma n2 divided by 2. Clear? So if you see somewhere that if x1 follow gamma with n by 2 degree of freedom or n by 2 parameter, n by 2 parameter, if x1 follow gamma n by 2 parameter comma 1 by 2, and x2 follow gamma n by 2 comma 1 by 2, then the ratio of x1 divided by x1 plus x2 will also follow beta, as chi-square n is considered as beta. It's the special case of gamma distribution. Chi-square is special case of gamma distribution. In place of chi-square, if there is written that x1 and x2 follow gamma distribution, then also you can say x1 divided by x1 plus x2 will follow beta distribution. Clear? So in place of this, if x follow gamma, y follow gamma n by 2 comma 1 by 2, n by 2 comma 1 by 2, then you can say that it will follow beta, as chi-square is the special case of gamma distribution. Clear? So now let's prove this theorem. Proof. Same f of x1 comma x2, we will write the joint distribution n1 plus n2 divided by 2, n1 divided by 2 gamma n2 divided by 2 e raised power minus x1 plus x2 divided by 2 x1 n1 divided by 2 minus 1 x2 n2 divided by 2 minus 1. Clear? x1 comma x2 between 0 to infinity. Clear? Now let u is equal to x1 plus x2 and v is equal to x1 plus x2. So in place of x1 plus x2 we will write uv is equal to x1 and v is equal to x1 plus x2. Clear? So now Jacobian, that is j, that's simply v, Jacobian will be mod of v, as you can prove this by del x upon del u, del x2 upon del x1 upon del x, del u, del x1 upon del v, del x2 upon del u, del x2 upon del v. By this you can get the v, mod of v. Jacobian is always written in the mod. If there is minus v, then mod of minus v is equal to v. Then you have to replace minus v with v by taking the mod. Right? Whenever you see mod of anything, mod of minus anything, mod of minus a, that will be equal to a. And in case of joint distribution, whenever you take Jacobian transformation, then you have to put the mod If there is positive or negative values, then negative value will come as positive value. Clear? So now f of u comma v will be old function, that will be 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2 e raised power minus x1 plus x2 divided by 2 x1 n1 divided by 2 minus 1 x2 n2 divided by 2 minus this multiply Jacobian. So this will be equal to 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2 e raised power minus, what's x1? x1 is uv plus v. What's x2? Simply, what's x2? Wait a minute. What is my x1? What is my x1? That is uv. That is uv. That is uv. And what is my v? What is my v? What is my v? V is equal to x1 plus x2. Then v will be, if we see what's x2 here, x2 will be x1 minus v. So x2 will be x1. What's x1? That's uv minus v. That is v u minus 1. Yeah, 1 minus u. So this will be equal to mine plus, what's x2? That is v 1 minus u. Then this is divided by 2. x1, what's x1? That's uv. x1 is uv n1 divided by 2 minus 1. What's x2? That is v 1 minus u n2 divided by 2 minus 1 into v. Let me write this again. That will be equal to 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2 e raised power minus, this is uv plus v 1 minus u divided by 2 uv n1 divided by 2 minus 1 v 1 minus u n2 divided by 2 minus 1 into v. So let's rearrange the terms. So this will be equal to 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2 e raised power e raised power, what we will do here, can we take v as a common? So this is minus v upon 2, that's u plus 1 minus u. This is u n1 divided by 2 minus 1 v n1 divided by 2 minus 1, and this will be v 1 minus u n2 divided by 2 minus 1 into v. So see, I can write this as, this is equal to 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2 e raised power minus v by 2 u n1 divided by 2 minus 1 minus u n2 divided by 2 minus 1, and this is v n1 plus n2 divided by 2 minus 1. Clear? Now from this is 0, u comma v is less than this. So from this, if I need the marginal of u, that's f of u. I will integrate this function with respect to v from 0 to infinity. Now say f of u, that is simply f of x1 plus x2. This is equal to 0 to infinity u n1 divided by 2 minus 1 divided by 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2 1 minus u n2 divided by 2 minus 1 0 to infinity, that's 0 to infinity e to the power minus v by 2 u n1 plus n2, this is v, sorry, this is v n1 plus n2 divided by 2 minus 1 dv. So this is the constant with respect to v. This is the constant. So now this is equal to u n1 divided by 2 minus 1 minus u n2 divided by 2 minus 1 upon 2 n1 plus n2 divided by 2 gamma n1 divided by 2 gamma n2 divided by 2. So see 0 to infinity, and this will be equal to, this will be nothing but gamma n1 plus n2 divided by 2 upon, what will be this will be 1 by 2 n1 plus n2 divided by 2. So this will be equal to gamma n1 plus n2 divided by 2 upon 1 by 2 n1 plus n2 divided by 2. So this will be nothing but simply 1 upon beta n1 divided by 2 comma n2 divided by 2 u n1 divided by 2 minus 1 minus u n2 divided by 2 minus 1. So let's compare with the beta distribution with parameter a comma b. This is x, a minus 1 minus x, b minus 1. So this is similar to this. So u divide by u follows beta first kind. So u, that's equal to x1 divided by x1 plus x2 will follow beta first kind n1 divided by 2 comma n2 divided by 2, hence proved. So don't get confused over here. There is a simply cancellation of the terms. So we will left with only this. So this and this will cancel out, and we will be left with only this term, and this and this will go, right? See, the terms which will be cancelled out is, this is u n1 divided by 2 minus 1 minus u n2 divided by 2 minus 1. This is gamma n1 divided by 2 gamma n2 divided by 2, and this is gamma n1 plus n2 divided by 2, and this will go whenever this will we will say 1 by 2 is simply 1 raised power n1 plus n2 divided by 2, and this is 2 n1 plus n2 divided by 2 into 1 upon 2 n1 plus n2 divided by 2. This and this can also cancel out. 1 raised power something is 1, so we will left with only these terms. So this is equal to this, this is equal to this, right? This is equal to this. Now another theorem is derive the distribution of s square is equal to 1 upon n summation xi minus x bar square. I is equal to 1 to n if x1 x2 up to xn follows normal mu comma sigma square. So we need to find the distribution of this S square. That's 1 upon n summation xi minus x bar whole square. Now see solution. I is equal to 1 to n xi minus mu whole square will be written like this. I is equal to 1 to n xi minus x bar plus x bar minus mu whole square. What I did, I simply add or subtract minus x and plus x. So we will get back this. Whenever this cancel out, we will get back this. Treat this as a, treat this as b. Now expand. I is equal to 1 to n. This is a square x1 minus x bar square plus x minus mu x bar minus mu whole square, a square plus b square plus 2a b. Clear? 2a b. Since, or we can simply write this as xi minus x bar square plus summation x bar minus mu whole square plus 2 summation xi minus x bar minus mu this. Since sum of deviations taken from the mean is equal to 0, so this term will be equal to 0. So this is equal to summation xi minus x bar, and see this is constant, this is constant, x bar is constant, as mean is constant. See, here is the I is equal to 1 to n, the summation runs from 1 to n on this xi only. Clear? Here is no involvement of i's, so this is constant, this is constant. The summation will be converted into n. This is x bar minus mu whole square. This is summation xi minus mu whole square. I is equal to 1 to n. So say this is I is equal to 1 to n. ये लेक्चर देखने के बाद आप दोबारा से 2x स्पीड पे ये फिर से देख लेना. Then you will understand these things better. Now divide by sigma square. So this is summation xi minus mu whole square upon sigma square. I is equal to 1 to n is equal to summation xi minus x bar whole square plus can I write this as, or simply n by sigma square x bar minus mu whole square. See, what is this? What is this? This is simply chi square, or simply we can write this as summation I is equal to 1 to n xi minus mu upon sigma square, and this is square. This is equal to, and this is sigma square. This is equal to summation I is equal to 1 to n xi minus x bar whole square upon sigma square plus, can I write this as x bar minus mu upon sigma divided by under root n whole square. I can write this as, why? Because this is x bar minus mu whole square upon sigma square divided by n. So this is equivalent to this. So now see, what is this? This is my chi square n. This is my chi square n, and this is my chi square 1. Then what will be the distribution of this? This will be chi square n minus 1. So summation I is equal to 1 to n xi minus x bar square upon sigma square is equal to summation I is equal to 1 to n xi minus mu upon sigma whole square minus x bar minus mu upon sigma divided by root n whole square. So say this is my chi square n minus chi square 1. So the distribution of this will be chi square n minus 1. Chi square n minus 1. So we got distribution of chi-square n minus 1. Chi-square n minus 1. So remember, 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 this will be this will help you in the numericals. The numericals which will be asked in your GATE exam, IIT-JEE exam, CSI NET exam, or ISS exam. That summation xi minus mu upon sigma whole square will follow chi-square n only, and summation I is equal to 1 to n xi minus x bar upon sigma whole square will follow chi-square n minus 1, and summation xi minus mu upon sigma whole square, sigma upon or sigma whole square, simply if yeah, this is sigma whole square. So see, this is summation, or not summation, this is summation xi minus mu upon sigma whole square will follow chi-square 1. Clear? Will follow chi-square 1. Will follow chi-square. See, as you can see the difference, the difference is, here we took the standard deviation of x bar only, that is sigma square upon n. As you know, x bar will follow normal mu comma sigma square upon n. So we took the standard deviation of x bar, not xi. If I take xi, then this will be only sigma square, or sigma, standard deviation will be sigma, and this will be sigma square over whole. Again, this will also follow x bar minus mu upon sigma upon under root n whole square will also follow chi-square 1. Clear? So you need to remember these three things. Very much helpful, important. This is important. Clear? Now, see. Now, as I say, summation xi minus x bar upon sigma square will follow chi-square n minus 1. What will be the expectation of this? What will be the expectation and variance of this? If I say, what will be s square? That is summation xi minus x bar upon n. Then ns square is equal to summation xi minus x bar. So in replacement of this is ns square divided by sigma square follow chi-square n minus 1. Clear? So what's the expectation of this? Expectation of s square will be n, expectation of s square will be, expectation of chi-square n minus 1 is n minus 1. So expectation of s square will be n minus 1 divided by n sigma square. So this is expectation of s square is equal to 1 minus 1 upon n sigma square. And for large values of n, for n tending to large, expectation of s square is equal to sigma square. And similarly, what will be the variance of this? What will be the variance of ns square upon sigma square? That will be equal to simply nothing. This is 2n minus 1. As you know, you can see x follows chi-square n. Expectation of this will be n. Variance of this will be 2n. So simply variance of this will be 2n minus 1. So variance of this is n square, variance of s square divided by sigma 4 will be equal to 2n minus 1. So which implies that variance of s square will be 2n minus 1 upon n square sigma 4. Sigma 4 for large values, variance of s square will be 2 sigma 4 upon n. 2 sigma 4 upon n. Clear? 2 sigma 4 upon n. So you need to remember these things. These are very important for you. You need to remember these things.